Okay, once again we're covering Euclid Book 2, proposition number 9. And therefore we're going to go with, first of all, angle GEF is 45 degrees. Well, where's GEF? Well, here's G, here's E, and here's F, and it's 45 degrees. And we established this a long time ago. Now we can establish that EGF is equal to 90 degrees. Where is EGF? Well, here's E, here's G, and here's F. And it is 90 degrees because of Euclid Book 1, proposition number 29. Okay, that means we can also say that EFG is equal to 45 degrees. Well, here's E, here's F, and here's G, and it's 45 degrees, and we can say that because of Euclid Book 1, proposition number 32. So now we can say that GEF, angle GEF, is equal in size to angle EFG. GEF, EFG. These two angles here are equal in size. We can also go on to say that EG equals GF. Well, here's EG and equals GF. These two lines right here are equal because of Euclid Book 1, proposition number 6. We can also say that angle ABE is 45 degrees. Well, here's A, here's B, here's E. We already said at some point that this was 45 degrees. We can also now say that angle FDB is 90 degrees. Where's angle FDB? Well, here's F, here's D, and here's B. This angle right here is 90 degrees. And we can say this because of Euclid Book 1, proposition number 29. Then we can go on to say that angle BFD, which this is B, and this is F, and this is D, is going to be 45 degrees. And this is by Euclid Book 1, proposition number 32. That makes angle ABE, equal in size to DFB, DFB. These two angles are equal in size. And that also makes line FD equal to DB. Okay, and that, if I recall correctly, is from Euclid Book 1, proposition number 6. Alright, now if you'll remember, when you have two lines of equal length, and this was covered in Euclid Book 1, proposition number 48, and in a video called Euclid Supplemental, if you have two lines here that are equal in size, if you were to draw a square right underneath this line and a square underneath this line, which we're talking about lines AC and CB, then the area inside that square and the area inside this square would be exactly the same. Now, we're not going to draw out those lines for you today, but trust me, if you were to draw a square using AC as one of the four sides of the square and draw a perfect square here, and you were to draw another square between CB and the square underneath it would be well, CB would be one side of the square, and then you have three other sides that would be exactly the same like the CB. And I know I keep talking on and on and on, but the square underneath AC and the square underneath CB, their areas would be exactly the same. Okay, since that's true, we can say that the area between the area inside of AC and the area inside of CB, if added together, would be twice the amount of the area contained by AC. Okay. Now, we have EA. Where is EA? Well, here is E and here is A. This line right here, we have a square on it. Okay, I know you don't see it, but we have a square on it. And the square of EA is equal to the square on AC plus CE. So we have a square underneath AC and we have a square underneath CE. So the area inside of here will be the area inside of here and here added together. Okay, and that's by Euclid Book 1, proposition number 47, which is the Pythagorean theorem. So now we can go on and say, because AC and CE are exactly the same size, and the areas in these two squares would be exactly the same size, therefore, the area inside of square EA is exactly the same size as twice the area of AC. Whew. Alright, now that makes line EG equal to GF. Well, here's EG, okay, and here's GF. These two lines are exactly the same size. Why is that? Because of Euclid Book 1 proposition number 6. We can also say that the square over here on EG and the square underneath GF are exactly the same size. So, twice the area inside the square GF is going to be equal to the sum of the areas of square EG and square GF. Alright. Now, the square of EF, which this is EF right here, the square that we draw on EF, that area is equal in size to the addition of the square on EG and GF, which is from Euclid Book 1 proposition number 47. So the square of EF, that area, is the same amount as twice the area of square GF. Okay, so if we had a square here on EF, then twice the area underneath GF would equal the size of the area on EF. Whew. Alright. Line GF is equal in size to line CD. Where's GF? GF is here, CD is here, and the reason for that is Euclid Book 1 proposition number 34. The square of EF is equal to twice the size of the square on CD. Well, here's EF here. The square on it is equal to twice the size of the area contained by CD. Well, here's CD. Okay, so the area underneath here and the area of GF would be exactly the same. Alright, so the area contained by the square on EF is equal to twice the area of CD. And of course, the area of EA is equal to twice the area of AC. So let's first find EA. EA is here. The area contained by this square would be twice the size of the area of CD, which CD is right here, and it'd be twice the size of this. And we're not quite finished with this proof yet. There will be a part 3. Stay tuned.